Yep. So that's, yeah, it's going through. This isn't going through. Oh. I think we're up.
Yep. All right, you can start. Cool. I guess I'll just start by saying, can everyone hear me? Maybe just give me like a hello or like a thumbs up or something like that. Yeah, cool. Okay. Well, hello everyone on the live stream, and hello friend who's here in person. My name is Jordan, and I'm going to be running us through the second half of Math 2018/2019. So we're going to start from topic number 5, ordinary differential equations, or ODEs. So what is an ordinary differential equation? Well, obviously it's a differential equation. We all know what those are. So it's ordinary because there's no partial derivatives. We're talking about regular derivatives here, or ordinary. So we're going to start off with this first question, which shouldn't be too difficult. It should be pretty standard. So we've got the question here: x plus y by dy dx is equal to e to the power of 3x minus x minus y. And we've got some initial conditions over here. Let's just test if this pen works. Yeah, cool. All right. Great. So if we move forward, there we go. So from this term on the left, we can see that because these two here are being multiplied together, so we can see that it's not linear, right? So because it's not linear, then we think through all the different options that it could be, and we go, okay, well, let's see if we can solve this by separating the variables. That's probably going to be the first step we take. And without like exactly knowing what to do, I can see that over here we've got this guy and we've got this guy, right? And they look pretty similar. So my approach is going to be, let's try and figure out a way to tackle them and then see if that can lead us to a solution. So that's exactly what's happened here. So as you can see on the right hand side, take the negative sign out, so then we can group these together. And now we can see that these are actually then the same expression on the left and the right. So then I bring that over to the left-hand side, and then now we can factorize that out. And so we're left with this expression right at the end here. Now, our approach is to separate the variables. So we can see that this equation now is separated kind of into like 3 little sections, right? We've got section 1, section 2, section 3. So now, section 3 is only a function of x. Section 1 is a function of x and y. And we've got this middle section here, which is our derivative. Now, my approach is going to be, let's try and find a substitution that can turn section 1 into one variable. And if we choose one that's clever enough, we'll be able to get rid of this one term here, so that we've just got the derivative of both the variables we're talking about. So again, so we'll have one variable on this side, in this part. We'll have another variable over here, which is our x. And then we'll have the derivative of both of them, which will turn it into then a separable equation. Get rid of all these drawings. So if we go to the next slide, do I have it on this side? I think that's just exactly what I was saying then. Yeah, so we're going to use a substitution to try and turn that left-hand side into one variable. Cool. So the substitution we're going to use is v is equal to x plus y. So again, turning that whole thing into just one variable that we can tackle. And then if we look at the derivative of that function, so dy by dx, right? We're turning this, so if we turn that into y equals v minus x, so did that right? Yep. So we substitute that in here and we take the derivative of that, and that's going to give us this expression here. So then what we do is we substitute v equals x plus y, and then we substitute this new dy by dx value. Or we can rearrange it here and sub it in differently, but either way, what that's going to do is that's going to take us from here down to here. And so as you can see, well, now we've got exactly what we're looking for. We've got this, it's just one variable. We've got the derivative of both of them in the center, and then we've got the other variable on the right-hand side. So now we've successfully separated them into 3 different sections. I just put a little footnote at the end as well. A common mistake is to substitute in for x using this expression as well, but then that's kind of like pointing you back in the wrong direction, because then you've got two other variables on this side, and then you're just in an endless loop of trying to solve this equation. So we get to here, we move forward. We're going to integrate both sides with respect to x. Not exactly what happens. We can imagine they just cancel, and then you get to this. We integrate. I'm sure we all know how to integrate these functions. These aren't too crazy. Then we get to this. We have a constant of integration on the right-hand side. It's important not to forget that, because we got indefinite integrals. Great. And then so we've got to this expression here. And then now what we originally had was a function of x and y. So we substitute back in, we get this. I've got this little dash above the c because this constant is not the exact same constant as this one, but in the end, it's all just the constant of integration, so it's not too important. But we can see that this is actually equal to that, just in case you're wondering how we got from c to c dash. Great, so yeah, so we've done that integration, which has led us back to this when we substitute back in. Now we want to get rid of this constant of integration. In general, like, you wouldn't have to, because we've solved the ODE, but we've been given some initial conditions, so we may as well use them to try and get the full answer. So if we use our initial conditions, we substitute in x equals 0, y equals 2. We solve through that, we find our constant, and then we sub it back in, and then we have our solution. Cool, so that's our solution to the first order differential equation. Cool. If there are any questions in the chat, let me know. Do you have any questions about that one? Pretty straightforward, right? Cool. Great. Let's move forward. Also, anyone in the chat, or obviously yourself as well, if I'm moving too fast or too slow, just let me know. Cool. So now we're going to move over to second order differential equations. So this is like kind of probably more what you're going to be dealing with more often in the exam. It says use the method of undetermined coefficients to solve the second order differential equation, and it gives the equation. And then you have initial conditions. You have an initial, you can think of it as like an initial displacement and initial velocity, because we've got that y term, and then we've got the y dash term. Then there's also like a little bit of a follow-up, which we'll see how we go for time with this one. If we get time, we'll chuck that in as well. But those are just a couple of extra things on the end there. Great, so the first step, always when you're dealing with these kind of things, find the homogeneous solution. So we find the homogeneous solution by making the right side equal to 0. So if you want to think of it, we're going to get to this kind of stuff in a second, but if you want to think of it as like, this is like your forcing function. So like this is describing a sort of like mass spring vibration state, and then you've got your forcing function here. So we're going to say, well, let's look at the case where we don't have any forcing function, and it's just in free vibration. So we're going to look at that first, and then we'll apply it afterwards. Great, so we find the homogeneous solution. So the first thing to do that is find the characteristic polynomial. And I'm sure at this stage you all know how to do this, but just a quick rundown in case you're not sure. So we substitute in y equals e to the lambda t. The reason we do that is because that's a function that works really well with derivatives. So we substitute that in, and then, yeah, so we substitute that in, and then we get the characteristic polynomial, which is this guy here. So because we end up with a state where either that's equal to 0 or our solution for y is equal to 0. But if we say our solution to y is equal to 0, well, that's not very interesting. So we say that's a trivial solution, then we try to find the non-trivial solution. So the solution of this characteristic polynomial is lambda 1 is equal to -1, and lambda 2 is equal to -2. And that's because this guy over here, whoops, if I can fix my handwriting, is lambda plus 1. Oh, I can't go off there. Oops, let's try this again. Lambda plus 2. Yeah. Cool, and then that's how we get our lambda 1 and lambda 2. So then, we see that lambda 1 and lambda 2 are real and distinct. So we've got a couple of cases that you can be in. You can be either real and distinct, they can be real and two of the same, you can have complex. So yeah, if you're not sure like how to get from this part to figuring out that this is your general, your homogeneous solution, just substitute in you've got the general form, which is your y homogeneous is equal to e to the alpha t cos beta t plus sine beta t. Right, so this is the general form, right? And either you'll have like a version where it's just the exponential part or just the cosines and sines, or you could have a case where it's all of this. The reason we get to that is because we found these lambda 1s and lambda 2s, which can be any complex number. So if you put e to some complex number lambda, this is the most general form that you can get. And then when you've got real and distinct roots, you won't have to worry about this part, you'll just have this part. So that's why we get two exponentials there in the homogeneous solution. So yeah, so the message there is like, if you get confused, just substitute your lambdas back into your initial guess for y, which was here. If you get confused, just substitute them back in and then expand from there, and then you'll get your homogeneous solution. So we've just put a and b, because we're not sure what multiples of that we have. Then moving forward, we're going to try and find the particular solution. So now to find the particular solution, it's similar in the fact that we want to try and find the most general form of it that we can. So we look at this function on the right, and then we say, okay, well, how can we find the most general form of that possible? So we've got this exponential term, and so the most general way we can define one of those is that we have c times e to the minus t2. So it still needs to be minus 2t, sorry. Still needs to be that, but we find the generality by putting the c at the front. And then here we see we have a degree 2 polynomial of t, and then we put this here as the most general form of that degree 2 polynomial. So this is then our particular solution for y. Then I've just calculated here the first and second derivatives, because they're going to come in handy later. Well, actually, right now. So I've calculated those. So the top one's our particular solution, then the first and second derivative. And then what I do is I substitute these into here to find which exact particular solution we want to look at. So I substitute them in here. And as you can see, I've done this long substitution here. And then what I've done is then made that equal to the right-hand side. So if we go through solving, if you just write out, like go slow, take your time, write it out carefully, and then just you want to find all the like terms, and then we find out that this is the particular solution that we're looking for. Based on this forcing function, that's the one we're looking for. Great, so now our general solution is our homogeneous solution, our particular solution together, which means that, oh, not this one yet, this one. That's our general solution, combining the homogeneous and particular solution. But you can see we've still got these constants a and b. And we're going to use the initial conditions here to get rid of those, which is similar to what we did for that first order one. So I've calculated this just to help us out. That's not part of the solution, but that's going to help us in the next one, where then we substitute in and we find our constants a and b, and we find out in this case a equals -9 and b equals 8. Then we put that back in, and then this, finally, after all of that work, that's what y is equal to in this instance, based on this second order ODE. Great, cool. If there's any questions about that, please let me know, because this is very important, and it's going to help us later on with some of the other stuff that we're trying to cover as well. Cool, so yeah, please let me know. Yeah, what about here? Any questions about that one? No? Yeah? Cool. Sweet. Let me think. Is there anything else I need to say about that? No, I think that's pretty straightforward. Oh, something else to say about that is about when you sub in your initial conditions. So I actually made this mistake many times when I was doing this course. I would sub in my initial conditions here, which will give you a slightly different answer. But I double check this with the solution as well. And so you want to find the general form and then substitute your initial conditions at the end to find the answer. Because otherwise you're not taking into account the particular solution when you find these constants a and b. And then to check that, you can also like substitute, where is it? Yeah. To check your answer, you can substitute it back in and make sure you get what you need and substitute the initial conditions if you want to double check. Cool. So it says also describe the steady state solution. So just quickly, so that is we're looking at what happens as like time goes to infinity. Obviously, we're not going to think about when it actually gets to infinity. Well, it can never get to infinity, but we want to see what happens as we approach that. So we can see that these exponential terms here, right? So you can think, actually, where's my solution? Yeah. You can think of these exponential terms. So e to the negative t is obviously the equivalent to that, right? And then so as time goes to infinity, that means that this number is going to blow up, but means this whole thing is going to tend to 0. So then these guys are going to go to 0. And these guys, you can say, well, these guys are going to go to infinity. So you're not really finding anything. But like I said before, we're not actually thinking about what happens right as we get to infinity. These guys are going to get to 0 a lot faster than these guys are going to blow up. So when we say find the steady state solution, we're cancelling off these exponential terms and we're saying that this is then our steady state solution. So after a long amount of time, once everything in the system has had time to settle, this is going to be what our steady state solution is. And that's what I've just written there. Yeah. So yeah, thinking about, like I said before, like thinking back to that idea of like this is describing like an oscillation, like a vibrating system, and this is our forcing function. We can say like this is what happens initially, and then after some time these terms cancel out and we're left with this to describe the system. Cool. The Wronskian formula, I can never say that word. This is just a formula that is usually provided to you, but it's not that difficult to memorize. And then, yeah, so we've got our, where are we? Yeah, here. So we've got our y1, y2, y-1, y-2. Those are pretty easy to calculate based on your two different solutions. So you can see here, this is the form that we're looking at. So you just substitute those in, calculate the determinant, and this will give you the Wronskian, just in case you need to do the variation of parameters method that comes into play there. Cool. Last little thing on ODEs, I'm pretty sure, before we move on to the next topic, is forced oscillations and resonance. So we're kind of already talking about oscillations in the last one because this topic is very interrelated. Oscillations are very important to consider. Yeah, they occur in everyday life, like music even. There's vibration. Great. So this question here, a freely vibrating system is represented by this ODE. And as you can see here, the number here is not specified. We've just put a constant C. So the question is, what damping constants C produce overdamping, critical damping, underdamping, and no damping? Great. So as you can see, as listed in the question, there's 4 different types of damping. So there's 4 different cases we can be in. So if we think about, let me see if I can just draw a little thing here. Right, so if we've got a system, right, and just say, actually, let me draw it like this instead. If we've got something that's oscillating like this, right, that's freely vibrating. Now we can introduce damping, and what will happen is then potentially we can have damping like this, which is like pretty gradual, which would be critical damping. We can have overdamping, which would then, let me see if I can do it on the same one. We can have overdamping, which would bring it down much quicker. We can have underdamping, which would let it oscillate for some time. Or we can have no damping, which would be that original case where it just oscillates freely forever. Great, and the way we find that is either you can just memorize this formula, which is, so you can memorize the different versions of this formula if you want to, but it just comes from before when we were solving the characteristic equation of the system. So overdamping would be if c squared is greater than 4mk, where m is this constant, which is the mass constant, and k is the spring constant over here. And then we've got critical damping is when they're equal, underdamping is when it's less than, but c is greater than or equal to 0, so it can't be less than 0. And then no damping is when there's just no constant here. So it just looks like y double dash plus 4y equals 0. Great. So in our case, we do actually have numbers to substitute in here. So we substitute those numbers in, and we find that these are the cases for each one. Cool. That one's not too difficult. But here's what we really want to look at. So we've put a 5 instead of that c, and we put a forcing function on the right-hand side here, or it's called driving force in the question. So it says, describe the y displacement of the system over time. Great, so we start off like we just did before. We find the characteristic equation. We get this characteristic equation this time, which gives us lambda 1 equals -1 and lambda 2 equals -4. In these sort of instances, you're going to see like negatives because we're looking at exponentials that decay over time. So it's pretty common to see negative signs. So again, similar to 4, we have this. Moving forward, then we guess our particular solution, which is the most general form of this that we can take. So the most general form of a sine 2t is a linear combination of cosines and sines. So we get this is our particular solution, and then find the first and second derivative, again, like we did before. Just interestingly to note, this second derivative is always going to be equal to negative this guy squared times the particular solution. Not sure if you would have noticed that or if it's been brought up, but yeah, it's cool to note. Then we move forward. We solve for our constants again. Now, this is our general solution here. And then I'm pretty sure the next slide will give us some, so the next slide then gives us some initial conditions, and we're going to use those to find our constants A and B again. So we've got y0 equals 1 and y dash of 0 equals 0, which is our initial displacement and our initial velocity. So I substitute those in, and then I find A and B, which is A is 32 on 15 and B is -8 on 15, which I then put in to get our final solution y. Great. So sorry if I rushed through that a little bit fast, but it's pretty similar to the previous question that we did. It's just putting it in a more like real world application. So that's what I was trying to say before, where it's like, it's all pretty interrelated. It's all pretty similar. Then it asks us to find the steady state oscillations. So the response to the system after a sufficiently long time. And like we did before, we say that these are going to go to 0 a lot faster than that. Well, actually, this one here won't ever go to 0 because it just goes cos is less than 1, and then so that term there will always be less than, or the absolute value will always be less than 3/5. So then we say that, our steady state solution is then just this last term, and make sure you include the minus sign because that's important as well. Cool. Oh, and then I just tag this little question on the end of this little topic. So we've just rearranged that equation that we had before, this guy, and we did what I was saying where we have no damping. So if we get rid of the damping, we have this equation here, y double dash plus 4y is equal to 8 cosine, and then it's got this little argument in here. And it says, which values of omega will the system achieve resonance? So the reason I've included this is just because resonance is an important thing to remember, and it's just a simple definition. So resonance will be achieved if we have a forcing frequency that matches a natural frequency. So we've already solved this kind of equation, and we found that the natural frequencies are at 2t, or the natural frequency, is when omega is equal to 2. So then what we do is we say, well, when will 2 on this left-hand side equal to 2 pi omega on the right-hand side? And we solve that, and we find that when omega is equal to 1 on pi radians per second, then that's when we'll achieve resonance. So so what that's saying is like the system has natural frequencies that it can vibrate at, and then when you force the system to vibrate at that frequency, you get amplitude that just keeps increasing until you achieve possibly catastrophic failure. Cool. And that's the end of the ODEs topic. So I'll just pause for a second in case there's any questions. And then we'll push forward into Laplace transforms. Cool. All right, let's push forward into Laplace transforms. If there any questions arise on ODEs, still you can still put them in the chat, or you can still ask, and I'll be more than happy to answer them. Great. So Laplace transforms. There's a bunch of information here about Laplace transforms. I'm sure hopefully you're all familiar with what a Laplace transform is. Hopefully you've been using it the past term. So like what we're doing with Laplace, well, if you do this course, MATH2018, you're going to be using Laplace transforms a lot. So what we're doing here is we've got our, sorry, I'm struggling to write this down. That's meant to say spatial. And then we've got time. So if these are our spatial and our time domains, we get given something to solve. Then what we do is we use our Laplace transform and we take it into the time domain, right? And then in the time domain, we solve it. So this is our solving. Because here we can use algebraic expressions to solve it, whereas here it's a lot more difficult. Then what we do is we take our inverse Laplace transform to bring it back to the spatial domain, and then this is our answer here. So that's basically what we're doing with this whole topic. We're finding something that's really difficult to solve, bring it over, we solve it in the time domain, then we bring it back, and that's our answer. Cool. So this is covering the Heaviside function. I thought it would be I thought it would be better if we do a proof with this, because using the Heaviside function, we're going to be using it later, and also it's not too difficult on its own. So I thought we'll step it up a little bit. Use the integral definition to prove that the Laplace transform of the Heaviside function is equal to this expression on the right. So obviously this is given to you in your Laplace transform table, but we're going to prove it. So this is the integral definition of a Laplace transform, so that all the formulas in the table that you have, this is how they're all figured out. Just taking the integral of your function multiplied by this exponential, and that gives you the transform. Great. So we're going to start off by just using that definition from the last slide, and we're going to substitute our function in. And then, so this slide actually doesn't really do much. We're just splitting up our integral into more achievable pieces. So we start off at the top. Then I'm going to split that into two different sections. So the reason I split that is because if we think about what the Heaviside function is, it's kind of like a switch. It's kind of like an on-off switch. So you've got some function that turns on as soon as you hit A. So this is our point A. Our function is off, and then we hit A, and then whatever the function is, whatever we want that function to be, turns on there. Obviously, this is not a function, or maybe it is. I don't know. Maybe that's for you to answer. But yeah, it turns on an A, which is the important part. So A is a critical point here. So we split up the integral around A. Whoops. There we go. We split it up. So we've got from 0 to A, and we've got from A to infinity. And then, because this is an improper integral on the right here, so then I'll just take the limit as B goes to infinity and put B up here. And so now at this point, we're ready to proceed forward. So we've gone from here, which is not really achievable, and then we've gone to here. Now, on this next slide, so we use what the definition of the Heaviside function is. So again, remembering that it's 0 until it hits A, and then it switches on, and then it becomes 1 times whatever your function is, and it becomes whatever the function is normally. So if this is 0 to A, it means we're in the before case. So this is just equal to 0, so we can disregard that. This is on the post A section, so it's equal to 1. So it'll be 1 times this, so we calculate what this integral is. Now, actually, I've just replicated what I already did. We just want to calculate what this integral is. Cool. So on the next slide, you'll see we calculate this integral. So this integral is not too difficult to do. Luckily, a lot with this course at least, there's a lot of it in engineering too. We work with like exponentials, which are really nice when it comes to derivative and integrals. So we get this expression, we substitute in our values, and then we take the limit as B goes to infinity. So as this goes to infinity, as we talked about before, it's like we're talking about this. So as it goes to infinity, this one goes to infinity, but then the overall expression then goes to 0. So we get rid of that, so I'm not distracted. Great, so then that's going to 0. So we're only considering the second term because that's independent of b. And then, lo and behold, that's the original expression we're looking for. Thank God. If it wasn't, something would be definitely wrong. So yeah, so that's the proof there of just how we get to that. And like I said, like all the things in the table, this is how they're found, just through a short little proof like this. Cool. Moving on. So now we're going to do some calculation. So find the Laplace transform of this function here, t squared times the Heaviside function turning on at 3. So we see that there's a cut at t equals to 3, but we haven't got our shift in the corresponding function. So as you know, these things have to come in pairs. So if you've got a cut, you also need a shift. So we're going to introduce a shift into this t squared, so that way we can actually use this Laplace transform properly. Because like I said before, you could go from first principles and just integrate it and find it that way, but that's probably going to take a lot longer. And given you're trying to do an exam, you don't want to be working with complicated integrals. So the easier way is to just make this in the form that we already have in the table. So we turn this t squared into something that has a combination of t minus 3's. So we can't just stop here. We can't just forget about these guys, because a times t minus 3 squared is just going to be a and then t squared minus 6t plus 9, right? You're going to have these terms here that aren't going to want to cancel. So then what we need to do is we need to introduce some lower order terms as well, so we can cancel in a clever way that works for what we need. So we expand this out, and then we say, well, a must be equal to 1, like comparing left and right hand side. So if a is 1, then this is minus 6. This whole expression here must be equal to 0 because there's no t term on the left. So if that's 0, we move the 6 over. So then b must be 6. And as you can see, b is 6 here. A is 1 there. Then we know that this must be 9. Then this is minus 18. 9 minus 18 is minus 9. Again, this whole guy is equal to 0, so we move that over. C is equal to 9. So now, again, like I said a couple of times, t squared is now in a form that works for our purposes here, because we've got the cut and the shift. So what we do is then we substitute our new version into the expression here, and then we just apply the linearity of the Laplace transform. So what have I done here? Yeah, great, yeah. So I multiplied the Heaviside function to each little term, which gets me term 1, term 2, term 3, and then I split them up using linearity, and now I've got this Laplace transform, and this Laplace transform. Great, and then this is that shifting theory I was talking about, where in order to use it, we need the cut here and the shift in the function. So that's the one we're going to try and use. So now we've got functions which are powers of t. You can kind of, at this point, when you're trying to figure out which Laplace transform to use, you can forget this for a second and just look at what this is. So this is t squared, this is t to the 1, and that's essentially t to the 0, or 1. Great, and we can see, so they're all powers of t, so we're going to use this function here, where it's t to the power n. So we're going to flick back and forth between this side, the next slide, and this slide for a second. So looking at this first one, so up to here was on the last slide already, and then I just took the constants out. So looking at the first term, we got t squared, so then n is 2, so that's 2 factorial over s to the power of 2 plus 1. And we can see here 2 factorial, s to the power of 2 plus 1. Then this is t to the 1, so that gives us 1 factorial, 1 plus 1. And then you can think of this as t to the 0, or I think there's one on the table that works for just 1. So you substitute those in. And now that's how we get these 3 things here, right? But it's important to remember we have to put this out the front according to our shifting theorem. So because this is t minus 3 squared multiplied by the Heaviside function at t minus 3, we need to use this shifting theorem and multiply another exponential at the front of each of them. And that's what we've got here. And the 6 is just the constant that was attached, and the 9 was a constant attached. So then that's how we get these 3 terms. And then we can just, if we want to, we can rearrange and factorize, and we get this over here. Cool. So yeah, so it's pretty cool. So like you consider this, which would be pretty difficult to do via integration, and you just manipulate it a little bit, and then you can use all your results from the tables. Bless you. Now we're going to go backwards. We're going to try an inverse Laplace transform. So it's a similar principle, but something we use a lot more often in inverse Laplace transforms is partial fractions, right? So going from spatial to time domain using the Laplace transform, you've got a lot of exponentials, a lot of polynomials that you're trying to convert. Going backwards, it's just a lot of linear fractions. Cool. So let's get started. So to get started with this one, first off, I'm going to ignore this. I'm just going to consider this on the left of the inside the inverse Laplace transform. I'm going to consider that first. And then I'm going to think about how I can then use the shift afterwards. So that's pretty much what I just said there. So the way we do that, if you're not sure how I got this expression here, so you can think of like, this is what we have in the question. So using partial fractions, we're going to say like, how can I turn this into A, which is A is just a constant, over the first term. I'm just going to write over this for a second and I'll rub it out. And then another constant over the second term, right? And then if I multiply this on both sides, then that's how I get this expression here, which I'm sure you're all familiar with, but just in case. So I get this. Now I look at the case when s is equal to 1. So this guy disappears. This guy turns into 9. This guy turns into 2. And then I solve that for a. And then similarly, I do the same thing when s is negative 1. So that disappears. This becomes negative 2. And this becomes, what's that? Negative 6, is that right? Yeah. And then, so then b is 3. So now we've got our a and b. So therefore, we've turned this fraction into 2 partial fractions, which is a lot easier then to apply the Laplace transform, because then we have expressions for these in the table, whereas we don't have an expression for that. Cool. So moving forward, all I've done is just substitute our partial fractions in. Then I expand down to here, and then I apply linearity, and then I separate them into 2. And then what have I done between this step and this step? It doesn't look like I've done anything. That's right. I think we can ignore this one. And then I've just taken the constants out the front. Cool. So again, all I've just done with that first bit, and it's something I'd recommend, is just like rearrange, apply linearity, just get to a form that you're comfortable working with, do all of that first, and then think about using the table. Because I think it's just a lot clearer that way. Because I know when I was like first learning this, it was very confusing. Like you're trying to, in your head, retain that you have to use a shifting theorem, and then I'll have to introduce a cut, and you're trying to hold that in your brain, and it's just a lot sometimes. So yeah, it's better to get on paper this expression because it's a lot clearer. So now that we've figured out this guy, or almost, we've got to do one more thing. Now we can start thinking about this e to the negative 5s term. So again, using our shifting theorem, our second shifting theorem to be more specific, we know that when we have this in the time domain, it's going to introduce a shift when we get back to the spatial domain. Cool. So like we did in the previous question when we were using the Laplace transform, we want to introduce, so we've got our cut essentially, that's like the equivalent in the time domain. Now we want to introduce the shift. So I just turn the partial fractions that we had here, so these partial fractions here, right? I want to turn them into shifted versions. So I introduce that shift, and these are all equivalent. So let's consider that one at a time. Let's do the first one. So the first term, which this term is found here, that's this whole thing. Sorry, it's getting a bit muddled. It's getting a bit crazy there. Yeah, so that's that term. So we put our shifted version of the fraction in there, right? And then I just convert this into minus 6, because in the table, this is how the formula is given. So it's given as S minus A. So we've got our S and our minus, this is our A, and then we bring it over, and then we see, using this formula, we get e to the minus 6t, and we've got our 3 at the front. And then, like I said, because we've got our shift and our cut, we times it by the Heaviside function, turning on at 5. Cool, and then we do the same for the second term. So it's exact same process. We've got our shift, you've got our constant, we use the formula, bring it over, and this is our second term. Then we bring it back, we just add them together. So the inverse Laplace transform of this guy is then this, which is those first and second terms put together. Cool. I'll pause for a second in case there's any questions about that, because there's, like I said, there's a lot of moving parts to Laplace transforms. Cool, let's keep going. So we're talking about Laplace transform and systems of ODEs. So we've got these two differential equations. If it helps, I think I write this later on, but if it helps, you can think of this as just x dash, and this as y dash, if that's more familiar to you. So we've got these two ODEs, and we've got some initial conditions here. Great. So moving forward, it doesn't specifically ask in this question to solve using Laplace transforms, but because we're in this topic, we will. So it's just up to you. If you get presented this question in the exam, you can choose whatever's the most efficient way for you personally to solve it. I think Laplace transform is actually really efficient once you get used to how it works, because you almost memorize the table by accident, and then you can just work through really fast. So we're going to use a Laplace transform like we did 2 questions ago. And let's consider the first one first. Why not? It's called the first one for a reason, right? So we take the Laplace transform of both sides, and then I haven't really applied any transforms. I've just, again, used linearity. And like I said in the last question, just get it to a form where you feel comfortable with. And like that, see, to me, like that's super clear. Each term's got its own Laplace transform. Super, super clear. Great. Let's move on to the next slide. Yeah, cool. I'll talk about this here. So what we're going to do is we're going to introduce some notation, which I'm sure you're familiar with. So the Laplace transform of lowercase x is just going to be equal to big X or capital X. And the same for y, just because that happens on the next slide. Oh, actually it happens here down the bottom. So we can see the Laplace transform of nothing is nothing. 10 times the Laplace transform of y. And then we've got the same for 4 times x. Now we've got this derivative. So again, we just use our formula that we know. So this is essentially like x with the first time derivative. So what we're doing, we can see that this function terminates when s is to the power 0. So we're just going to keep churning through this formula until we get s to the power 0. So we have s to the 1, because our n is 1 here, times the Laplace transform, so that's what we've got here, s to the power 1 times our Laplace transform, minus s to the power 1 minus 1, which is 0. So we've hit 0 here. So essentially we can ignore this, because this would be the second derivative and the third and fourth and so on. Excuse me. So sorry. So yeah, we can stop here. And then that gives us s to the 1 times the Laplace transform minus nothing, or 1 rather, times the initial value of x, which here we can see is -1. So we bring this formula over to the next side. We substitute in -1, which then turns this into a +1, so we have this expression. And then what I do is I just rearrange, so we've got an x times something, a y times something, and then something on the other side. So there's a 1 here, which means we have to remember this equation. So we'll come back to this one in a second. We do the exact same process for the second expression over here. Exact same thing. We apply linearity, get this, we do all the changes of notation, and then because this is the first derivative, it's the same thing, s times the Laplace transform of y minus the initial condition of y, which is 0. This is actually a little bit simpler, because then that disappears at 0. We rearrange down to here. Now, instead of stopping here, I'm going to take it one step further and make it in terms of y, because I want to substitute this into the first one that we found, which was here. So what I do exactly that, I substitute in, because I've got the Laplace transform of x and the Laplace transform of y are my two unknowns. So I've got two equations, so we simultaneously solve. We get this after doing a bunch of algebra, and then so we get the Laplace transform of x is equal to this. Great, so we're going to apply that idea that we talked about in the second Laplace question, and we're going to turn this into partial fractions. So we use the same process as before. We end up getting this expression. So we look at the case when s is 1. That gives us one constant. And then we look at the case where s is 6. That gives us the other one. So then we can say that then this expression is then equivalent to that, which is very useful because then we can use our tables. So then, is that right? Yeah. So then we apply the inverse Laplace transform to this. Yeah, I'll keep going through and then I'll talk about something in a second. So we can apply the inverse Laplace transform to that, which means that we work through, we apply linearity to get this, we move over to this, and then we just use the table. This is our where was it? Yeah, 1 over s minus a. That's the one we're looking at here. Yeah. So then that gives us e to the 6t, and then this one gives us minus 2 times e to the t. So we get our answer for x in the original spatial domain. Oops. Let me just rub these ones out. So we can go about this two ways. We can substitute this into one of these expressions. Actually, I think it'll have to be this one. We can substitute this into this one and find our function of y, or, which is the approach I'm going to take, we can go back to this and use this and substitute back in our expression for y over here to find our y, and then do the inverse Laplace transform again. Either way will give you the exact same result. I'm going to do it the second way that I mentioned. So we substitute back in. And the reason I did that is because I saw this term, where was it? I saw this guy, and I saw that this is going to then cancel with this guy for x and make it really simple. So we do that, and then we get this for y. So we're substituting back the Laplace of x into the Laplace of y. Then we get this, and then using the same process, we turn this into a partial fraction, or partial fractions. We turn it into partial fractions there. I'm going to get rid of that so you can see what it actually is. Then we apply the inverse Laplace transform to those separate fractions, and that gives us this. So we've got our x, which was over here, and we've got our y, which is over here. So again, like I said, just double checking. We can go, let's use this one. So you can say dy dt, which is minus 6, actually I'm going to need more room, minus 6 e to the 6t plus e to the t minus 5 e to the 6t, again minus 5 e to the t, oh no, sorry, that's x, that's what we're trying to find, minus 5x minus 11 there, minus 11 e to the t equals 0. Great. So if we simplify this, we get minus 5x plus 5e to the 6t. Yeah, then that's minus 10e to the t equals 0. Then we move it over. So then x is equal to 2e to the t minus e to the 6t. So let's just double check. And that's exactly what we've got over here. So the other way around, so those two terms are swapped around, but e to the 6t minus 2e to the t minus 6t minus 2. Hold on a second. I forgot a minus sign somewhere. Oh, that's why. Sorry about that. Accidentally put a minus sign on both sides. So then that would be, yeah. And that's the exact same thing we got before. So you can do it either way. In both ways, it'll come out the same. Cool. And then I didn't do exactly what I did there, but what I did is I just substituted in left and right hand sides and hope they were equal. But it's just checking that you got the right answer. I'm someone who like overchecks in exams, and likes to always have methods to back up what I'm trying to find. So I think it's pretty useful to have just a second way to ensure that what you've calculated is the right thing. Cool. So topic 7 is Fourier series. We might take like a couple minutes break. Let's say like 3 to 5 minute break, so everyone can like get a drink of water or go to the bathroom, and then we'll get started with the last two topics. Cool. See you in a sec. How's it going? Is it doing all right? It's a bit quiet. Oh. Do you feel like I'm going too fast at all? Is it all right? Okay. Yeah, there's a lot of content. Do you have any questions about anything today or anything at all? Yeah. There's a lot of little details. Like you learn about, like, you still do the variation of parameters method, right? So I wasn't sure because I remember doing that, but I couldn't find any questions on it in the past few papers. So maybe that might be a sign that one's coming up this year. I don't know. Yeah. You got yours on after mine at 5, right? For the 2 111. You pumped? You excited?
Not really, but once I finish that, then could finally start studying programs.
Yeah, same. That's me. This. What?
I'm also going through Fourier series.
Pardon?
I'm also going through Fourier series in teacher.
Oh, actually? Oh, because they're like equivalent.
Yeah.
Yeah.
I think the ODEs stuff, like some of that is covered in like
222. Ah, yeah.
Yeah, but we don't like the past stuff.
Yeah, because I remember John was saying, like, when we were trying to divide the topics, he's like, you have to do that one because he hadn't learned that one. It's like, yeah, it gets used a couple of times in a couple of different engineering courses. It's pretty useful. What math courses did you take this term?
2301, computing and optimization.
Oh, cool. 2301, mathematical computing, and 3521, algebraic techniques in number theory. Yeah, I really like 3521. Your battery.
I haven't charged it before.
How do I check? Do I just escape this?
This seems fine.
Yeah, it'll make it the last hour.
Yep.
Cool.
I can just plug it through.
Just in case,
Let's
maybe.
just plug it now.
Yeah. Cool. Well, maybe let's get started again, just so we have enough time to get through everything. Yeah, because we started late. Hopefully, I tried to catch it up, so I don't think we'll have to go over, but who knows? We'll see how it goes. Cool. Let's get stuck into Fourier series, which I think, personally, is a very interesting topic. Just a little tidbit about my own personal interests. Cool. Again, here's some, because these slides are going to be available afterwards, right?
Yep, on the website.
The slides will be available on the website. So I put like a couple of extra things, and like I said at the beginning, like, there's a couple of extra parts to each question that I've kind of glossed over. So yeah, if you want to like download that and have a look at this extra information, it might be useful as well. So there's a question. Oh, Gerald. You should have taken 3521. No, I'm pretty sure 3711 was useful as well. Cool, let's get stuck in. So another proof. I tried to include, I included this and the other proof because it's not often they asked to prove these things, but like, may as well overtrain for it, in my opinion. So yeah, so we're going to prove that this left-hand side is equal to this right-hand side. I'm not even going to try saying them because they're very ugly. This is also known as Parsifal's identity, just in case you're interested in that kind of stuff. So let us prove this. The general form of a Fourier series, I hope I'm saying that right, Fourier, it's a very difficult word to say for me. But yeah, so this is the general form. So for a function f with a period 2L, we have this expression here, right? And so we've got our constants. So these are the little parts that we're always trying to find. These constants, A0, AN, BN. Luckily, we have these formulas for them over here. I'm sure you're all familiar with this, but just a quick little overview before we get stuck in, because we're going to use it a couple of times. So, for this proof, so we start off with, let's consider just the left-hand side. So we have the left-hand side, just rewritten exactly there. Then I'm going to turn this f of x squared into two versions of f of x. So it's equivalent, it's the exact same thing. We just split them up. Then I'm going to turn one of these f of x's into our Fourier series. Because like I said here, we're trying to find, we're finding a really good approximation of some function by using a linear combination of sines and cosines. Right, and our approximation is so good that we're going to say that it is f of x. We're going to put it in there. And then what I'm going to do is I'm just going to expand. So I say a naught times this thing. A naught times f of x all within the integral. This times f of x in the integral. And then all of that, I expand those out. I'll get rid of this so you can see. Expand those out. And then now going on the next slide, we're going to consider this term first. Actually, just to note as well, I've taken that a naught all the way out, which may have been a bit too fast to do that, but nonetheless it's fine because it's independent of x, so we can just bring it out the front of the integral there. Great. Oh, I just noticed as well, there should be a dx here and a dx here, just because these integrals are separate now. Great, so just to clarify, I've turned this f of x squared into two f of x's and just expanded, and this is what I get. Now we're going to consider this term first, then this one, and then this one. So we go to the first one. So we look at this first term over here. I'm going to pretend like this is 2 over 2L instead of 1 over L, which is equivalent, and then instead I bring that 2 over here. So now I've got 1 over 2L again, should be a dx here. I think that's going to be a recurring thing. So just imagine there's a dx at the end there, times this integral. Well, if we go back to here, we notice that that's our definition of what a naught is. So we say that that's a naught over here, and then we multiply those together, because we can do that within the real numbers, and then we get 2a naught squared. Great, so that's our consideration of the first term. So we're looking like we're on the right track, which is good. Then we go to the second term, and we're going to do the same trick. So we've got this term here. Now, what we're going to do is we're going to assume that we can swap out the location of the sum and the integral. Again, because we've got our ANs, which are independent of x. So we're going to bring that out. We pull it out at the front and we swap it around. Then we get to this. And then again, we can see, oh, actually, from here, we can see that that is our definition of what AN is. Let's just double check that. So 1 on L, integral from negative L to L, f of x, cosine n pi on L, x. If we memorize that really quick, we can see that's exactly what AN is. So then we get the sum from 1 to infinity of AN squared, and that is this one right here. So again, we're still on the right track, which is good. When we look at the last term, oh, this should say second as well. Sorry, there's a bunch of typos. In the third term, it's the exact same process as we did for the second one, except this is B instead of A. So you run through, you get the exact same thing. So we bring them all together, we add them up. Then what we can do is we can combine these AN and BNs because they're running the same summation and they both rely on n. So we can bring that into the same summation, and then that gives us this, which is exactly what we're looking for. Thank God we made it. We got to the end of this proof unscathed, which sometimes doesn't happen. Great. So that's that little proof there. I know like sometimes proofs are a bit annoying, so if there's any questions, please let me know. Moving forward, so we've got our periodic extensions. So we've got the 3 different types. You can just shift by L. So for example, if I had a function that looks like, actually I should draw that axis a little bit more like this. You know what, let's go attempt number 3. There we go. If we have a function that looks like this, we can just shift it by L and just keep doing that. That's meant to be a vertical line. Yeah, we can just keep shifting by L. If we have this, we can reflect it over the y-axis, so we get this, and then we can repeat it with a period of 2L, so we get something like that. Or, if we got this, we can reflect it over the origin, so we get something like this, and then what we do is then we shift it, and then we get something like this, which goes on forever. So correspondingly, they're called just a periodic shift, an even shift, and an odd shift. Whoops. There we go. Cool. So we've got a function defined here. So it's 1 when it's between 0 and pi on 2, and then it's 0 when it's between pi on 2 and pi. So it says it wants us to sketch the even periodic extension of f on the interval negative 2 pi is less than x, less than equal to x, less than equal to 2 pi. So if we do that, so it's exactly what I was just saying before. So what is this? 1, so if we call this pi on 2, this is our origin, this is pi, this is 1. So between 0 and pi on 2, so we got this, and then open circle, and then between pi on 2 and x, we got closed circle, open circle. Great. That should be pretty straightforward. Again, for any questions, even about like the little open and closed circles, let me know. Then, what we want to do is we want to calculate the Fourier cosine series of f. So this notation, I noticed it's like interchangeable within all the exams, like even or like cosine or odd or sine. Yeah, it interchanges a lot. So I wanted to include it here just so we remember like what it means. So when we're calculating an even extension of this. So by construction, we're looking for something that's even. So we know from the lecture notes that when we're looking for something that's even, so we've got our A naught plus summation an cos plus, I know this is not exactly what you get, but just as a rough little thing, right? When we're looking for something that's even, this term is always going to be 0. So we don't even need to worry about calculating it, because that's just going to take up time in our exam that we could use for other things. So all we need to do is calculate A naught and an, and then we'll be done. And we'll have our Fourier series. Yeah, and then from our sketch, we know that our period is 2 pi, right? Excuse me. So then 2 pi is equal to 2L, which means that our L is going to be pi. Cool, so we've got all the information we need. Let's move forward. Start solving. So first up is A naught. Again, we just use a formula. Let me actually, instead of flicking back, I'll just write it here. So we've got 1 on 2L here, f dx. That's f of x. Cool, so we know L is pi, so we can easily substitute that in, and we put the pi's here. Great, and then this one remains the same. Moving through, so because this is an even function, right, we're integrating all the way through here. Now, because it's even, we know that it's going to be symmetric about here. So we can say that instead of integrating across these two regions, we can just integrate across one and then multiply it by 2, because that's going to save us some time and some energy. So then we change the limits, and then we put a 2 out the front, which is going to cancel there for us. So then we get 1 on pi is then equal to this integral. And I'm going to split this integral up even further. You don't need to do these steps, but I'm just going to run through these because these are really useful tips and tricks when it comes to more complex integrals as well. And now I can see that because of our definition, it's going to be really useful for us to consider what happens before and after pi on 2. So the first term is going to be from 0 to pi on 2. And the second term will then be the remaining pi on 2 to pi. Cool. So again, like we did for Laplace transforms, we've brought this down into something that we're comfortable with working with. Moving forward, then we just evaluate. So between 0 and pi on 2, actually we'll stay here, we've got 1, that's great. Between pi on 2 and pi, we've got 0, so that goes to 0. We're just considering this integral. The integral of 1 is hopefully not challenging. If it is, that's okay, still ask. But we integrate that and we get here, pi on 2 and 0 are our limits. Then we substitute in, multiply by pi, so that gives us that A naught is a half. Cool, so we've already got one of our terms.
So I think the 1 should turn into x.
Say that again.
The 1 should turn into x.
1 should turn into x.
Integrate.
Oh yeah, you're right here, hey. That one? Yeah, sorry about that, that's a bit of a typo. Thanks. Guys, you can thanks Gordon for that one. Cool. So let me just run through that again, just in case that was a bit confusing. So we cancel this one out because that's 0. When we integrate this, so this should be x because we've actually integrated it now. And then we substitute in, and then we multiply by pi. And then we get a half. Cool. Sorry about that. So moving forward, let's go for an now. And it's going to be a very similar process, except just the formula is different. So I do a similar process here, where because it's even, then I bring it down here, I multiply the 2 out the front. This time we don't get a cancellation because there's no 2 there. But alas, we move forward anyway. And then we have our split integral there. Cool. Moving on, have I done the same thing here? No, I did it correctly here. That's good. So we split it. We apply our definition again. That goes to 0. Then we integrate this function here. And then we substitute in, which I've done on the next page. Yep, I've substituted in here. Okay, so now here's the crux of it. This is the part that took me forever to get my head around. And I finally did it, and I was very proud of myself. Because for me, it was very challenging. So this is sine of 0, which we can disregard because that's 0. So something that really helps me is if you draw up this This is all stations, the central guy, where we have your, what is it? All that stuff. Yeah, you can continue the rest. Yeah. Cool, so I like to draw that. Well, actually, I just think about that in my head, and this really helps me wrap my head around this next part. So sine of 0 is 0. So we're considering this. So sine of n pi on 2. So we want to think about what is n pi on 2? So what is the sine of n pi on 2? When does it equal 1? When does it equal minus 1? When does it equal 0? So I've given the answer. I've given you the answer here, but I've got an explanation on the next slide. So let's just have a look at this answer first. We cancel, and then we get to here. That'll be 0. So this is our answer here. But on the next slide, we have a bit of an explanation. So if we look at all the different cases, for these values of n, we'll get 0. For these values of n, 1, and these ones, negative 1. Now, we can see that all the even n are going to give us 0. So n is never going to be even within our Fourier series. So we can consider when n is equal to some odd number, 2k plus 1, where k is free to run from, let's say, from 0 to infinity. Because if we say, let me check that's right. So if k is 0, then that gives me 1. Yeah, cool. So let's go from 0. So that's going to give me all the odd numbers, right? So then that's going to take into account these two cases, but we've still got to consider whether it's a positive one or a negative one. So what we introduce as well is we introduce this negative 1 to the k term, because we can see that when k is equal to 0 or 2 or 4 or 6, when it's all these even numbers, it's going to be in this case here. So minus 1 to an even power will give us 1. And then when it's all the odd k, that's not an odd number, that's an odd number, it's going to give us negative 1. So we want an odd power to negative 1, which gives us negative 1. So that's how we convert. Wait, let me separate for a second. That's how we convert this into our result, which is this. Right? And I'll go back to the last slide as well so you can see. What have I done? Ah, that's why. Sorry, because I took the n out and I confused myself. Yeah, because this should be 1 on n as well. So the n is only going to be an odd number. So we put it into this 2k plus. We put in this 2k plus 1, and then when we put the 2k plus 1 in here as well, that tells us that we've got minus 1 to the power of k. Cool. And then when we resolve all of that, we get a to the n, but now n is 2k plus 1, is this expression here. So that's how we find a to the n, which is no longer a to the n. Cool. There's a lot of moving parts there, so please let me know if any of that was not clear, and I can double down into any of that. Or if there's any questions in the room as well, please let me know. Cool. I'm just taking my time erasing this just in case there's any questions. Great, so now we've got a0 and an. We just put that into our formulation of the Fourier series. And so this is our a0. This combined with this is our an. And then we've got this. This was our n pi on Lx, because L is pi. Those will cancel. So then that's just nx, and n is this. So that's why we have that in there. And yeah. And also important to remember, last thing is k goes from 0. Remember, we started k from 0. So then, yeah, that's how we get that Fourier cosine series. Cool. All right, moving forward. Oh, actually, the one little last bit on this. Do I want this up? Or let's... Yeah, so what value will the Fourier cosine series converge at x is equal to pi on 2? So this is a common question that pops up, just like a little add-on at the end of it. So the trick here is that if you substitute pi on 2, so when you substitute it in, you're going to see that this is always an odd multiple of pi on 2 within the cosine. So it's in the argument of the cosine, right? And then that's going to give you 0. So then if we look back at this, then this is going to become 0. So then all we got to do is just look at this. So using the wording of the question, at x is equal to pi on 2, the Fourier cosine series will converge to a half, which is a0. Yeah. Or you can look at the graph as well, and you can see that that half will be the midpoint between, the half will be either the point or the midpoint where it's discontinuous at pi on 2 as well, from memory. Cool. Okay, so we're doing great for time. I might just pause for like a second and see if there's any questions for that, because that can be a little bit confusing sometimes. Actually, I'll leave this up in case there's any questions about this. Something I would recommend in preparation for the exam is like, just with these, do a bunch of different cases of Fourier series to calculate. Do one that's an even extension, do one that's an odd extension, do the whole process, just go through finding all the constants, because it's like a very procedural thing. So once you just get the practice of like, I find this, then I find this, then I find this, yeah, you're going to feel super comfy with it. And getting used to like how you find this part as well as this, but that was added on afterwards, but mainly this. Getting used to that process, it takes a bit of time, but once you've got it, it's super quick. You'll like get used to all the different cases that pop up. You'll just be able to replicate it pretty quickly. Hopefully, at least, that's the goal. All right, cool. Let's push forward into the last topic. So, partial differential equations. So we've already looked at ordinary differential equations. These are not solved in the exact same way, but there's a lot of similarities between the two. Again, they're all differential equations. As engineers, PDEs are very important. You're going to see them in so many different places, no matter what area you're doing. I've listed a couple here: fluid, solid mechanics, quantum mechanics, electromagnetism, so many different places. Cool. What I'm going to do is I'm going to go to this question first, because this question is going to take a while. So I'm going to run through the heat equation question, go through the whole thing for that, and then if we have time at the end, I'm going to go back to this wave equation question. Because the process of doing this question is very important. There's a lot of content in here that you're going to need to know, a lot of processes you're going to need to know. So we'll spend a lot of time here, and then we'll get to do an additional extra if we have time at the end. Cool, let's jump on in. So the temperature in a bar of length pi meters satisfies the heat equation du dt is equal to d squared u over dx squared. Or d. I think technically you meant to say du or dt or something like that. Where u of x and t is the temperature in degrees Celsius, t is the time in seconds, and x is the distance in meters from the left-hand side of the bar. Both ends of the bar are maintained at a temperature of 0 degrees Celsius. Hence, so this is one end of the bar, and that's the other end of the bar, so both ends are 0 for all t. And then, assuming that this is the form of the solution, we're going to show that this expression is true. So the way this question has been done is it does some of the work for you in that it guides you through the solution. And this happens a lot in the past exam papers. It guides you through each step and what you're wanting to do. In case it doesn't do that, it's important to know the steps already yourself, but we're lucky in this instance that it helps us through. So we're going to show that this is true. I've just condensed that question a little bit, just so we have space. So where do we start? Well, we have, this is the form of the solution that we're asked to assume. Even if you're not asked to assume it, this is a very useful form to guess. So we're going to substitute that into our heat equation, which was up here. I'm going to substitute that in there. So this is our U, and this is our U here. Now we take the derivatives as per usual. So this is a function of x, this is a function of t. So when we do our derivatives on the left-hand side, this is what we get. And then for a similar reason on the right-hand side, this is what we get. So we have those two expressions there. Now, what we can do is we can move the g of t and the f of x over to the opposite sides, and then we get this expression. Now, if we look at this expression, we can see that this is only a function of t. We've got 1 over g of t and g of t again differentiated with respect to t. That's only a function of t. Similarly, this is only a function of x on this side. So because we've got a function purely of t equal to a function purely of x, the only way we can relate those two things is if they're some sort of constant. That's the only way it can happen. So we call that, this is the separation constant. We're just going to call that k, just for the purposes of this. We're going to call it k. Great. And so actually that's the answer to the first part of this question. Sorry, I was ready to like push on through that full steam ahead. But that's the answer to the first part of the question. So important to remember is that because this is only a function of t, and this is only a function of x, that's why we get that result. And then just the bits in between were just little bits of differentiation. Cool. All right, moving forward into the next part. So the question says, now assuming that only k less than 0 yields non-trivial solutions, and set k equal to negative p squared for some p greater than 0. So let's just pause there for a second. So it says assuming that k less than 0 yields non-trivial solutions. What if it doesn't tell us to assume that? In the question, if it doesn't say to assume that, unfortunately, you're going to have to prove that that's the case. And the way you prove that that's the case, the most straightforward way to do that is you go, well, what happens when k is equal to 0? Solve through that and you'll find, oh, this leads to some contradiction. We can't have this case trivial, or usually actually it's just trivial solution. It's just usually if this is 0, well then u is 0. And then so you do that and then you look at k greater than 0, and then that one will either lead to a contradiction, or most likely again it'll say like, oh, then we have a trivial solution where u is equal to 0 again. So if it doesn't tell you to assume this, go through the other two cases, show that it has to be this, and then it'll most likely be this. Cool. So now that we're in the case where it is k less than 0, it's asking us to set k equal to negative p squared for some p greater than 0. Now, applying the initial conditions, show that p is equal to n, where n is equal to 1, 2, 3, all of the natural numbers, and that possible solutions for f of x are this expression. So much notation here, and I'm not sure why this step, this step is necessary in the sense that it clarifies like what we're talking about now, but there's a lot of different moving parts. So let's just like go slowly through this. From the previous slide, we can see this. Well, why can we see this? So if we look at this expression here, actually if we look at this whole equation there, so if we multiply the f of x over, we've got d squared f on dx squared is equal to k f of x. Now using different notation, we can call this f double dash of x is equal to k f of x. Now moving this over, we can say that f double dash of x minus k f of x is equal to 0. Sorry if that's a bit messy, but hopefully the point has got across that if we rearrange this, because we prove this is true, if we rearrange this, then this must also be true. And that's what's written here. Now we do as been told in the question, and we set k is equal to negative p squared. And this is kind of like revealing some of the truth as to why this is true, right? Like if we think about, without going too deep into it, if we think about like what we've learned about ODEs from the topic 5, I'm pretty sure it was, that I did at the beginning of this seminar, like we get to this expression and we can see like why they've told us to assume this, because then this turns this into a positive, and then we've got this plus this is equal to 0, and then this is going to lead us to some solutions that are going to work given the physical constraints of what's happening. Yeah, I'm not going to say like I'm trying to be a little bit ambiguous so you can still like go think about it, but that's kind of revealing some of the truth there. Great. So now because of what we know with ODEs from topic 5, this is our general solution for f of x. And if making this jump feels a bit odd or feels a bit rushed, just take this and then apply because this is a homogeneous equation. So go apply the characteristic equation, all that kind of stuff, and then we'll get to here. Perfect. Yeah, and we can see this using our knowledge of ODEs. So this is our general form of f of x. Now we're going to apply some boundary conditions. So we have those boundary conditions that said the plate at both ends is kept at 0 degrees. So we apply those boundary conditions here, and then we end up with this. So we can actually kind of ignore this, and we just want to think about this here. So for both, let's maybe just look at this one first. Right, so f of 0 times g of t is equal to 0. So one of those must be 0. If the right-hand side is 0, one of them's got to be 0. So let's think about g of t. So if g of t is 0, that means it's 0 for all t greater than 0. Well then, because we've assumed that u, how am I going to write this? There we go. Because we've assumed that u is f times g. If g is always 0, well then u is always 0, and that leads us to a trivial solution. So to obtain a non-trivial solution, we're going to say that this can't be 0, g can't be 0, so therefore f of 0, and similarly for the second one, f of pi must be 0. Something like, yeah, like I was kind of saying before, like with these kind of questions, they seem really like difficult and intricate, but the basic rundown of how these questions go is you start here, and then you just do like kind of like this, like the whole way down. Sometimes there's more branches. You just go, oh, this is trivial. Oh, this is trivial. This is trivial. And you just keep doing that, and you just keep like going through the woods, and then eventually you get to something where it's like, okay, this is the non-trivial solution of this system. So if you ever get lost as to what you're doing, just try all the cases out, and then you'll be able to eliminate a bunch of them that are trivial, and then you keep going forward. I feel like I said the word trivial like 70 times, but hopefully the point gets across. Cool. Let's go to the next slide. So, yeah, using this result, we found that f of 0 is equal to 0. So we remember we had, this is our general form of f of x. Right, now we know that f of 0 is equal to 0 and f of pi is equal to 0. So if we come over here, we see what that means for us. So we substitute 0 in here, and that means that a must be 0. Right, because this is 0, that whole thing becomes 1, that's 0, this whole thing becomes 0, that whole thing is gone. So a must be 0 as well. Well then, if we use this one, we get then this is pi, and then this is, actually that would not be 0, but this turns it into 0 for us because a is already 0, so that's gone. Sorry, I'm getting a bit messy now. That's all gone. So we're left with this. We're left with this term here is equal to 0. Now similarly to what we said before, either this is 0 or b is 0. Well, we're going to keep working our way down those branches that I mentioned, and we say, well, if b is equal to 0, well, that's a trivial solution, because then if a and b are 0, if a and b are 0, then f is 0. And then if f is 0, then u is 0. So again, we're in a trivial case. So we say, well, b can't be 0. So this must be 0. Well, if that's 0, then when is that 0? And I think that's what I look at on the next slide. Yeah, not on this one. So this is just saying that b can't be 0 because a is already 0, and that's going to lead us to a trivial solution. So we go to the next slide, and we say, well, when is this equal to 0? Sine of p pi. P pi is fun to say. This implies that p pi is equal to n pi, and the reason we say that is because for this to be true, p has to be equal to 1, 2, 3, all of those. It's something that took me a second to wrap my head around was why we don't start from 0. And the best reason I can think of as to why we don't start at 0 is because we cover that case like that case is already covered. You know what I mean? Because this is like a periodic thing, we actually don't need all of these n values. It kind of gives us the same thing, equal to 0. So, and that'll be apparent in a second. Like if that doesn't make sense, why we don't need all of these n, and why 0 is already covered, in a second it'll make sense. So we say that then these p values must be equal to these n values. So we set p equal to n. So then going back to our original notation, then k, instead of being equal to negative p squared, is now equal to negative n squared. So then our equation turns into, instead of f double dashed of x plus, instead of plus p squared, I think that should be squared. Yeah, going back to here. Yeah, so we're just replacing p by n, so that should be squared, is equal to 0. So the non-trivial solutions to this equation then are this, right? So we've said that, yeah, p must be equal to n, so we put that into there for n equal to 1, 2, 3, 4, 5, all the way through. Cool. Yeah, please stop me if any of this isn't making sense along the way. So we said that b can't be 0, so this has to be 0, and that's only 0 if we consider these n values. So then f of x is equal to this, when n is all of these numbers. Cool. So we've worked on f for a while now. So let's move over to g and get a corresponding solution for g, and then we can try and put them together to find u, which is what we're trying to do. This is our goal. This is what we want to achieve. So we do a very similar thing, except this time, because we already know this, so we get to this, because again, like before we have this is equal to k, but we know that now k is equal to negative n squared. So then rearranging this, we get a similar thing where we go g dashed plus n squared g is equal to 0, and that's what's written there. Oops. And then again, we can either think about it for a second and then jump to the general form, or if that's a bit too fast, then we find the characteristic equation and we can do stuff like that. Again, yeah. And then, yeah, so we get gn of t is equal to cn of t, where cn is just a constant, times the exponential times by t. Well, actually, that t should be up in there. So let me just rewrite this. So ignore that for a second. Sorry about all the typos, guys. I'm very new to LaTeX, so I'm still figuring out how to do this. Cool. So that's what we're looking at. Great. So we move forward. So now we've got a form of g and we've got a form of f. And so we know that u is equal to f times g. So we're going to substitute those in. So this is what I've done here. So I've substituted in f and g, and then I've created this new constant where d is just b times c. So for every iteration of n, I've just multiplied them together. Cool. So then this was our original part for f, and then this plus the c in there is our part for g. Great, so we've got a solution for each iteration of n. Now, because this is linear, we're going to use the principle of superposition, and we're going to construct the general solution. So instead of trying to find un, we're going to try and find u total. So we create a summation, and we're going to sum them all together, and that's what's done here. So we're just taking this, we're just adding them for every single value of n possible. Cool. Okay, so now here's what I was saying before, when I was confused why we start from, why we choose n equal to 1 as our starting point, because it has to be whole numbers, because this is useful for you but not for them. If you're thinking about the rotations around the unit circle, it has to be whole numbers, but why do we start from 1? So the reason it doesn't matter is because it's going to come out in here. So we use our initial conditions. Oh, okay, so yeah. It says, suppose the initial temperature distribution of the bar is equal to this. So it says at time equal to 0, right? This is our temperature distribution of the bar. So now this helps us find it. So if we equate what we've already found for u of x and t, and we take the time at 0, so you can see there was an exponential here, but because we've considered the time at 0, we get rid of that exponential, and we have this equation here. Now if we write out all the terms of this, we've got d1 sine of x plus d2 sine of 2x plus, and we've got from n equals 1 to infinity. And then if we equate both sides, we can see that the only ones we need to consider are d1 and d2, because on the right hand side here, anything times 3x or anything times 4x or anything times, actually now that I think about it, 0 would be silly, because then you wouldn't have any x at all. Well, my reasoning was right, but also 0x is just, we don't consider that anyway. Yeah. But yeah, so the point of what I'm trying to say is, you've got only 1 times x and 2 times x are the ones we need to consider. So therefore, the only constants we need are d1 and d2. So this simplifies things a little bit. So we know that d1 must then be equal to 2, and d2 must be equal to negative 16. Don't forget that negative sign, because all the rest of them are equal to 0. Hence, if we bring t back in and we take this infinite sum, the only terms that aren't going to be 0 are the first and second term. So u of x and t is equal to 2 times sine of x e to the negative t, because remember it was e to the negative n squared of t. So n equals 1 makes this 1, and n equals 2 makes this 4. So then we've got negative 16 sine of 2x e to the negative 4t. And yeah, so then that's how we get our general solution of u, of x and t. Cool. Let's just see if there's any additional... Yeah, okay, there's a little bit extra on the end of this question. But let's just pause there for a second and let's just talk about what we've done, because there's a lot of different processes that just happened. So, we get given a question. It says that the temperature in a bar satisfies this heat equation, and it gives us some boundary conditions. So with these kind of questions, you've got boundary and initial conditions. First of all, it tells us to get this, which we did. We found that these two expressions must be equal to a constant. So then, using the fact that we did that, we first try and attack f. And we say that, well, this must be true for f. Right? Then this is a helpful little tip, is to turn it into this. So then we can try and find the general form of f. So we're trying to solve f, which we're focusing on that at the moment. So now we apply the boundary conditions that we're given, because we found a general solution, but we've got some constants in there. So we do that, we apply our boundary conditions, and that helps us narrow down what f has to be. So then we say, well, then we thought f was this general thing, but actually we can be more specific and say that f must be this. And then we can be even more specific, or actually, before we get to that, we can say f must be this. But to get there, we have to say, well, this must be satisfied. And because b can't be 0, then this must be 0. So in order for that to be 0, we say that n must be these numbers here. So then, the most specific we can be is we can say that this f of x is equal to bn times sine n of x. Sorry, sine of nx. Cool. So we've gone down that route to find f. So then we jump back for a second. We try and find g. We do the exact same thing, but because in the heat equation, you've got this derivative, which is just du dt. And on this side, we've got the second derivative, which is d squared u. So it's similar, but it's not the exact same. Like in the wave equation, we have both second derivatives. Cool. So we go down trying to find the solution for G, but we get a different form for G. Actually, no, we want to look at this one. We get a different form from G than the one we got for F. So we bring them together because we notice that in the boundary conditions, sorry, I'm jumping around a lot, but in the boundary conditions, we don't have any boundary conditions for time because boundary conditions apply to the boundary of the system. So it's usually a spatial thing. So that's why we solve F first, because we can use those. We can't do a similar simplification here with G. So we just bring them together. And then the way we simplify now, instead of boundary conditions, is we use initial conditions. So using those initial conditions, then we say that these are the only terms considered, this one, and so that must be U. Just going to let that sink in for a second. Cool. So at the end of this question, it says determine all points X along the bar with a temperature of 0 degrees Celsius after T is equal to the natural log of 2 seconds. So it's a very specific time to look at. Like, I can't think of a time where I've ever needed to look at log of 2 seconds, but it makes sense why we pick that time. Because what we do is, so we're considering what happens at this time. So the easiest way to consider that is to substitute that in and see what that does to the system and what we have to do to X. So we know that the temperature is 0 at this time. So I substitute in the time and I say that the temperature distribution must be equal to 0. So, oh, sorry for the 2 equal signs. So we got 0 is equal to this. So this was our expression for U, as we can see here. This is our expression for U. And we just substitute in our time. Then we can do some simplification. So this guy here is equivalent to this, using our log laws, which is equivalent to this, which is then equivalent to this, because these two are inverse functions. So that's how we get that. And then we do a similar thing to get 1 on 16 over there. Now, they've done us a massive favor with the time that they've chosen, because we can see that exactly the exponential that we've just solved cancels exactly with the constant in front. So then we're left with this linear combination of signs. Then you can pick your own path to solve this, but the way I've done it is I've expanded this, and then I've done a little factorization, and then so we know that this is equal to 0, and then similar to how we've done before, we say, okay, well, what happens if this is equal to 0, right? So then if that's equal to 0, we can say that 2 cos of x is equal to 1, so cos of x is equal to a half, right? Sorry, it's a bit messy, but hopefully it's legible enough. Cos of x is equal to a half, and then so then x is equal to inverse cos of that, and we can say, well, that will be pi on 3. Now, you might be screaming at your computer, why is it not pi on 3 plus all the relevant periods? Sorry, I couldn't think quick enough off the top of my head. Well, hopefully you're not screaming at your computer screen, but if you are, the only reason we consider that is because if we go back to the original question, it's a bar of length pi meters, right? So the bar from here to here is only pi long. So if we were to consider, where am I? Yeah. So if we looked at this, so we've got pi on 3 right here. The only time, wait, is that right? Yeah. So we got pi on 3 here. Right, the only time we would ever get back to that again is if we went past pi. So that's the only one we need to consider for that case. Cool. Then we look at the other one. What about if sine of x is equal to 0? Then we can see that that would happen if we were here or if we were here, right? And then that would be 0 or if we were at pi, and that's these two here. So between 0 and pi, in this region here, you only get 3 solutions. So that means that if we draw our bar, right? And then if just say this is our origin, so we're saying this is 0 meters, and then it goes across to here, and this is pi meters. So we're saying at 0 meters, at pi meters, and roughly there, pi and 3 meters. So it starts off initially at 0 degrees, and then after natural log of 2 seconds, it's saying, actually, this must be a 1D bar. It's saying that at these 3 points, at this time, the temperature is still 0 degrees Celsius. So that's a physical interpretation of what it's trying to say. And I think sometimes it's important, because especially with these long questions where you have to do a lot of different processes and go through all these different things, it can get a bit confusing and you can forget about what you're trying to solve. So I think at the end, it's really good to just go okay, well, what is the physical interpretation of this? How can I draw this down? How can I draw this on the page and see what's actually happening, especially for engineering, because a lot of the time we're talking about specific real world things that are occurring. So yeah, I just think it's a really useful thing to just write it down at the end and go, well, what's actually happening? And it also gives you a chance to double check what you're doing. I know I definitely need that at the end of a long question like this. Cool. So that's the end of that question. I think what would be better to do, instead of going back to this question, right, because all of these partial differential equation questions have a lot of similar processes. They're all very linked together. So once you've once you solved all the way through one, you've got a pretty clear understanding of how to solve through other ones. The only thing that's different about this one is it tells you to assume this solution and work through that way. But aside from that, a lot of these are very, very similar. So I think in saying that, I think we'll wrap up there. And yeah, I'll say thanks to everyone for watching on the live stream. Thank you to our friend attending in person. Best of luck. There's still a few minutes, 2 minutes technically. But if you have any questions, please throw them in the chat. I'm more than happy to answer them. If you have any questions after this time, you can send them through on Discord or wherever, or ask some questions. Yeah. Cool. Thanks, guys.
Sounds good.